Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The morning of April 12, 1961, marked humanity's most audacious leap into the unknown. At Baikonur Cosmodrome in Kazakhstan, a 27-year-old Soviet pilot named Yuri Alexeyevich Gagarin prepared to become the first human being to orbit Earth. This moment represented the culmination of thousands of years of human dreams about flight, centuries of astronomical observation, and decades of rocket engineering that began with pioneers like Konstantin Tsiolkovsky and Sergei Korolev. The space race between the Soviet Union and United States had been intensifying since the launch of Sputnik 1 in 1957. That basketball-sized satellite proved that Earth's gravitational bonds could be broken, that artificial objects could be placed in stable orbit around our planet. But sending a human being into space required solving problems of unprecedented complexity. Life support systems, radiation shielding, precise navigation, and safe re-entry through Earth's atmosphere at speeds exceeding 17,500 miles per hour. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. Gagarin's selection wasn't accidental. The Soviet space program had systematically evaluated over 3,000 candidates, narrowing them down to 20 finalists who underwent grueling physical and psychological testing. These cosmonauts, as they were called, endured centrifuge training that subjected them to forces 8 times Earth's gravity, isolation tests in soundproof chambers, and complex simulations of emergency scenarios. The selection process revealed that fighter pilots possessed the ideal combination of physical conditioning, mental fortitude, and technical expertise needed for spaceflight. The mission's scientific objectives extended far beyond national prestige. Scientists needed to understand how the human body would respond to prolonged weightlessness, cosmic radiation exposure, and the psychological stress of complete isolation from Earth. Would blood circulation continue normally without gravity's assistance? Could the inner ear maintain balance and spatial orientation? Would cosmic rays damage DNA or cause immediate physiological harm? These questions had profound implications for the future of human space exploration. The Vostok 1 spacecraft represented a marvel of engineering efficiency. Weighing approximately 10,400 pounds, it consisted of 2 main sections: a spherical descent module, where Gagarin would spend his historic flight, and a service module containing life support equipment, attitude control systems, and the retro rockets needed for safe return to Earth. The entire vehicle was designed for automatic operation, since engineers weren't certain whether humans could think clearly or control spacecraft systems while experiencing weightlessness. Ground control maintained constant communication with Gagarin throughout the mission preparation. Radio telescopes across the Soviet Union stood ready to track the spacecraft's orbital path, while recovery teams positioned themselves along projected landing zones. The mission's success depended on precise timing. Earth's rotation meant that launch windows occurred only briefly each day, and any delay could postpone the attempt for weeks. As dawn broke over Baikonur, Gagarin suited up in his bright orange flight suit, designed to make him easily visible to search and rescue teams after landing. The suit incorporated a closed-loop life support system, backup oxygen supplies, and emergency communication equipment. Every component had been tested extensively, but theoretical preparation couldn't eliminate the fundamental uncertainty of human spaceflight. Gagarin was about to become humanity's first ambassador to the cosmos, carrying with him the hopes, fears, and scientific curiosity of our entire species. Yuri Gagarin's path to becoming humanity's first space traveler began in the small village of Klushino, located west of Moscow. Born on March 9, 1934, to peasant parents, Gagarin experienced the hardships of rural Soviet life during the 1930s and 40s. His childhood was interrupted by World War II, when German forces occupied his region for nearly 2 years. The young Gagarin witnessed aerial combat firsthand, developing a fascination with flight that would eventually carry him beyond Earth's atmosphere. After the war, Gagarin pursued technical education, studying agricultural machinery at a trade school before enrolling in the Saratov Industrial Technical School. However, his true passion emerged when he joined the local flying club in 1954. His instructors immediately recognized his natural piloting abilities and calm demeanor under pressure. These qualities led to his acceptance into the Orenburg Higher Air Force School, where he trained on military aircraft and graduated with honors in 1957. The Soviet space program's recruitment process began in 1959, following extensive analysis of pilot performance records throughout the Air Force. Candidates needed to meet stringent physical requirements: height between 5 feet 2 inches and 5 feet 11 inches, weight under 187 pounds, age between 25 and 30 years, and at least 150 hours of solo flight time. More importantly, they required exceptional psychological stability, as demonstrated through comprehensive testing protocols developed specifically for space exploration. Gagarin's selection from the initial pool of over 3,000 candidates reflected his unique combination of technical competence and personal characteristics. Psychological evaluations revealed his ability to remain calm during crisis situations, maintain clear thinking under extreme stress, and communicate effectively with ground control personnel. His fellow cosmonauts consistently rated him as someone they would trust with their lives, a crucial factor in the selection committee's final decision. The training program that followed pushed human physical and mental limits. Cosmonauts spent hours in centrifuges that simulated the crushing acceleration forces of rocket launch and atmospheric re-entry. These machines spun at velocities that created gravitational forces up to 12 times Earth's normal pull, causing blood to drain from the brain and making simple tasks like raising an arm nearly impossible. Gagarin and his colleagues also endured isolation testing in soundproof chambers, where they spent days alone, with minimal sensory input to simulate the psychological challenges of space travel. Weightlessness training presented unique challenges. Since sustained zero gravity couldn't be replicated on Earth's surface, instead cosmonauts experienced brief periods of weightlessness aboard specially modified aircraft that flew parabolic trajectories. During these flights, lasting only 20 to 30 seconds at a time, trainees practiced eating, drinking, and operating spacecraft controls while floating freely. The experience helped them understand how fundamental human activities would change in space, from the simple act of swallowing liquids to the complex task of spatial navigation without gravitational reference points. Technical training encompassed spacecraft systems, orbital mechanics, and emergency procedures. Cosmonauts studied the Vostok capsule's life support systems, learning to monitor oxygen levels, carbon dioxide scrubbing efficiency, and cabin pressure regulation. They memorized radio frequencies for communication, with ground control stations positioned across the Soviet Union, and practiced using backup systems in case primary equipment failed during flight. The final selection of Gagarin over his colleague, German Titov, came down to subtle differences in personality and physical condition. Both men possessed equivalent technical skills and physical fitness, but Gagarin's slightly smaller stature meant better fit within the Vostok capsule's confined space. Additionally, his consistently optimistic attitude and natural charisma made him an ideal representative for the Soviet Union's space program on the international stage. By early 1961, Gagarin had completed over 200 hours of specialized spaceflight training. He understood every system aboard the Vostok spacecraft, had practiced emergency procedures until they became instinctive responses, and had demonstrated remarkable composure during the most stressful simulations. As he prepared for humanity's first orbital flight, Gagarin carried not only the hopes of the Soviet space program, but also the accumulated knowledge and preparation that represented humanity's first serious attempt to become a spacefaring species. The Vostok spacecraft that carried Gagarin into orbit represented a masterpiece of early space engineering, designed under the leadership of Sergei Korolev, the Soviet Union's chief spacecraft designer. Unlike the capsule approach favored by American engineers, Vostok featured a distinctive spherical design that distributed atmospheric re-entry heating more evenly across its surface. This 3-meter diameter sphere, designated the descent module, housed all life support systems and served as Gagarin's entire living space during the historic flight. The sphere's construction utilized a heat-resistant ablative coating that would gradually burn away during re-entry, dissipating the tremendous thermal energy generated when the spacecraft encountered Earth's atmosphere at orbital velocity. Engineers calculated that without proper heat shielding, the capsule would experience temperatures exceeding 3,000 degrees Celsius, hot enough to vaporize most metals. The ablative material created a controlled burning process that carried away heat while maintaining structural integrity of the underlying pressure vessel. Life support systems aboard Vostok 1 required revolutionary approaches to maintaining human life in the vacuum of space. The cabin atmosphere consisted of nitrogen and oxygen at slightly below sea level pressure, reducing the risk of explosive decompression while maintaining adequate oxygen partial pressure for normal breathing. Carbon dioxide removal utilized chemical scrubbers containing lithium hydroxide, which absorbed exhaled carbon dioxide and prevented its accumulation to toxic levels. Water vapor was condensed and recycled, while trace contaminants were removed through activated charcoal filters. The spacecraft's electrical systems drew power from chemical batteries and solar panels, providing energy for life support, communications, and attitude control throughout the mission. Silver-zinc batteries supplied high current demands during launch and re-entry phases, while solar panels maintained continuous power during orbital flight. Redundant systems ensured that single-point failures wouldn't compromise mission safety, with backup batteries capable of supporting life support systems for several additional hours beyond the planned mission duration. Attitude control and orbital maneuvering relied on a combination of automatic systems and ground-based control. The service module attached to the descent sphere contained hydrogen peroxide thrusters that could adjust the spacecraft's orientation and initiate deorbit burns. When commanded from ground control, these thrusters produced relatively small amounts of thrust, measured in pounds rather than thousands of pounds like launch rockets, but provided precise control necessary for orbital operations. The R-7 rocket that launched Vostok 1 evolved from intercontinental ballistic missile technology, adapted specifically for space exploration missions. This massive vehicle, standing over 100 feet tall and weighing approximately 600,000 pounds when fully fueled, generated nearly 1 million pounds of thrust at liftoff. The rocket burned kerosene and liquid oxygen in its first-stage engines, achieving the precise velocity and trajectory needed to place the Vostok capsule into stable Earth orbit. Orbital mechanics calculations for Gagarin's flight required extraordinary precision. Engineers needed to achieve a velocity of approximately 17,500 miles per hour at the correct altitude and trajectory angle to establish a stable elliptical orbit. The planned orbit ranged from a minimum altitude of 112 miles to a maximum of 203 miles above Earth's surface, with an orbital period of approximately 89 minutes. These parameters ensured that atmospheric drag would naturally cause orbital decay within 10 days, providing automatic re-entry even if the retro-rocket system failed. Communication systems aboard Vostok 1 included both voice radio and telemetry. Transmission capabilities. Multiple radio frequencies allowed contact with ground stations across the Soviet Union as the spacecraft completed its orbital path. Telemetry systems continuously transmitted data about spacecraft systems performance, cabin environment, and Gagarin's physiological condition to flight controllers and medical personnel monitoring the mission. The ejection seat system represented one of Vostok's most innovative safety features. Rather than attempting a powered landing, which would have required additional fuel and complex systems, engineers designed the mission profile to have Gagarin eject from the descent module at approximately 23,000 feet altitude and parachute separately to Earth's surface. This approach simplified spacecraft design while providing pilot safety through proven ejection seat technology adapted from military aircraft. Navigation systems relied primarily on ground-based tracking and control, since onboard navigation, computers wouldn't become feasible until later space missions. Ground control calculated orbital parameters using radar tracking data and issued commands for attitude adjustments and deorbit burns via radio transmission. This approach concentrated complex calculations and decision-making at ground stations equipped with powerful computers and experienced flight controllers. At 9 hours 7 minutes Moscow time on April 12, 1961, the R-7 rocket engines ignited beneath Yuri Gagarin's Vostok capsule. The launch sequence had proceeded flawlessly, with all systems showing green lights as nearly 1 million pounds of thrust lifted humanity's first space traveler away from Earth. Gagarin's calm voice crackled over the radio. Poyakali! Meaning, let's go. Words that marked humanity's entry into the space age. The ascent phase lasted approximately 10 minutes, during which Gagarin experienced crushing acceleration forces reaching 8 times Earth's gravity. His specially designed flight suit included built-in compression systems that helped maintain blood circulation as the massive rocket accelerated through Earth's atmosphere. Ground telemetry showed all spacecraft systems operating normally as the Vostok capsule separated from its launch vehicle and entered its planned elliptical orbit. Gagarin's first moments in weightlessness came as a profound revelation. The feeling of weightlessness was somewhat unfamiliar compared with Earth conditions, he later reported. Here you feel as if you are hanging in a horizontal position in straps. You feel fine, and everything is easier to do. This initial observation provided crucial data about human adaptation to zero gravity, confirming that basic motor functions and cognitive abilities remained intact during the transition from Earth's gravitational field. The orbital trajectory carried Vostok 1 over the Soviet Union, then south across Africa and the Pacific Ocean, before returning north over the Americas and Atlantic. From his unique vantage point, Gagarin became the first human to observe Earth as a complete system. "The Earth is blue," he radioed to ground control. "How wonderful, it is amazing." His descriptions of our planet's appearance from space provided the first eyewitness account of Earth's atmospheric envelope, continental boundaries, and the sharp contrast between Earth's vibrant colors and the absolute blackness of space. Communication with ground control stations occurred intermittently, as the spacecraft's orbital path brought it within range of different tracking facilities. Soviet engineers had positioned monitoring stations across their territory to maintain contact throughout most of the orbital flight. These communications served multiple purposes: confirming spacecraft systems' performance, monitoring Gagarin's physiological condition, and gathering his observations about the space environment and Earth's appearance from orbit. The spacecraft's automatic systems controlled all major flight operations, including attitude adjustments and the critical deorbit burn. This design philosophy reflected uncertainty about human capabilities in weightlessness and ensured mission success, even if the pilot became incapacitated. However, Gagarin remained alert and actively monitored all systems throughout the flight, providing valuable feedback about human performance during spaceflight that would influence future mission designs. Midway through the orbital flight, Gagarin conducted simple experiments to understand how everyday activities change in weightlessness. He practiced eating specially prepared food, drinking liquids from squeeze tubes, and writing notes while floating in his restraint system. These activities, trivial on Earth's surface, required completely different techniques in the absence of gravity. Food particles and liquid droplets would float freely, if not properly contained, potentially damaging equipment or creating breathing hazards. The deorbit sequence began approximately 1 hour and 15 minutes after launch, when ground control sent commands to fire the retro-rockets. These engines, mounted on the service module, reduced orbital velocity by approximately 500 feet per second, just enough to lower the spacecraft's trajectory until it intersected Earth's atmosphere. The burn lasted 42 seconds and required precise timing and orientation to ensure landing in the designated recovery zone. Atmospheric re-entry subjected both spacecraft and pilot to extreme conditions as kinetic energy converted to heat. Through friction with air molecules, the descent module reached temperatures of approximately 3,000 degrees Celsius on its outer surface while maintaining comfortable conditions inside through ablative heat shielding. Gagarin experienced deceleration forces up to 10 times Earth's gravity, as atmospheric drag rapidly reduced the capsule's velocity from orbital speed to terminal velocity under parachutes. At approximately 23,000 feet altitude, following the planned mission profile, Gagarin activated his ejection seat and separated from the descent module. Both pilot and spacecraft descended under separate parachute systems, landing within minutes of each other near the city of Engels in the Saratov region. Recovery teams reached Gagarin quickly, confirming his excellent physical condition and the complete success of humanity's first orbital spaceflight. The total mission duration of 108 minutes transformed humanity's relationship with space from theoretical possibility to demonstrated reality. Ground telemetry confirmed that all spacecraft systems had performed nominally, while medical monitoring showed that human physiology adapted successfully to the space environment. Most importantly, Gagarin's detailed observations and calm performance throughout the flight proved that humans could not only survive in space, but actively contribute to space exploration missions. Gagarin's historic flight provided humanity's first comprehensive data set about human physiological responses to space conditions. Medical monitoring equipment aboard Vostok 1 continuously recorded his heart rate, blood pressure, breathing patterns, and body temperature throughout the mission. These measurements revealed that while initial adaptation to weightlessness caused temporary disorientation, basic cardiovascular and respiratory functions remained stable during orbital flight. The absence of gravity created immediate changes in blood circulation patterns that had concerned medical experts before the flight. On Earth, the cardiovascular system constantly works against gravity to pump blood from the legs back to the heart and brain. In weightlessness, this workload disappears, potentially causing blood to pool in the upper body and head. Gagarin's medical data showed initial increases in facial blood flow, causing slight facial swelling, but his cardiovascular system quickly adapted to the new conditions without compromising his ability to think clearly or operate spacecraft. Systems. Radiation exposure presented another major concern for mission planners. Earth's magnetic field and atmosphere protect surface dwellers from most cosmic radiation and solar particle emissions, but spacecraft traveling above the atmosphere encounter significantly higher radiation levels. Dosimeters aboard Vostok 1 measured Gagarin's total radiation exposure during the flight, recording levels approximately 100 times higher than normal background radiation on Earth's surface. While this represented a significant increase, the short mission duration kept total exposure well within acceptable limits for human health. The space environment's most immediately noticeable effect involved the complete absence of gravitational acceleration. Every human movement, from reaching for controls to turning one's head, required adaptation to weightless conditions. Gagarin reported that fine motor control remained unimpaired, but actions that relied on gravitational feedback, such as pouring liquids or judging distances, required conscious adjustment. His successful operation of spacecraft systems demonstrated that humans could maintain adequate performance for complex tasks during short-duration spaceflight. Sensory perception changes in weightlessness provided fascinating insights into human neurological adaptation. The inner ear's vestibular system, which maintains balance and spatial orientation on Earth, receives conflicting signals in zero gravity. Visual cues become the primary reference for determining up and down, but these references constantly shift as the spacecraft orbits Earth. Gagarin experienced mild spatial disorientation initially, but reported that the sensation diminished as his brain adapted to rely more heavily on visual orientation cues. Bone and muscle physiology represented long-term concerns that couldn't be fully evaluated during Gagarin's brief flight. However, medical experts understood that prolonged weightlessness would likely cause bone density reduction and muscle atrophy, since these tissues normally adapt to gravitational loading. The mission provided baseline data for comparison with longer flights, establishing medical monitoring protocols that would become standard for all subsequent human spaceflight missions. Psychological factors proved equally important for mission success. Complete isolation from Earth's surface, combined with the alien environment of space, could potentially trigger anxiety, depression, or panic responses that might compromise mission safety. Gagarin's calm demeanor and positive attitude throughout the flight demonstrated remarkable psychological resilience. His radio communications remained clear and professional, while his detailed observations of Earth from space showed maintained curiosity and intellectual engagement with the unique experience. The space environment's effect on basic biological functions like eating, drinking, and waste elimination required careful study. In weightlessness, liquids don't pour and solid foods don't fall into containers as they do on Earth. Gagarin successfully consumed specially prepared foods and liquids during the flight, proving that nutrition could be maintained during space missions. However, his experiences highlighted the need for specially designed food packaging and consumption techniques for longer missions. Sleep patterns and circadian rhythms presented additional concerns for extended spaceflight. Although Gagarin's mission lasted only 108 minutes, future missions would require astronauts to sleep in weightlessness. The absence of normal day-night cycles during orbital flight, with sunrise and sunset occurring every 90 minutes, could potentially disrupt natural sleep patterns and affect performance on longer missions. The mission's scientific data collection extended beyond human physiology to include observations of Earth's atmosphere, weather patterns, and geological features from space. Gagarin's descriptions of cloud formations, atmospheric layers, and continental boundaries provided valuable information for meteorologists and Earth scientists. His ability to make detailed visual observations while simultaneously monitoring spacecraft systems demonstrated that human crews could effectively serve as scientific observers during space missions. Temperature regulation in the spacecraft environment required careful attention to both equipment cooling and human comfort. The vacuum of space provides no mechanism for heat transfer except radiation, making thermal control systems critical for maintaining appropriate cabin temperatures. Vostok 1's environmental systems successfully maintained comfortable conditions throughout the flight, validating engineering approaches that would be refined for longer missions. These physiological and environmental data from Gagarin's flight established the foundation for all subsequent human spaceflight medical research, proving that humans could not only survive in space, but maintain the physical and mental capabilities necessary for complex space exploration missions. The announcement of Gagarin's successful orbital flight sent shockwaves throughout the international community, fundamentally altering perceptions of technological capability and national prestige. Within hours of the mission's completion, news organizations worldwide reported the historic achievement, with many emphasizing the Soviet Union's dramatic lead in space exploration technology. The flight demonstrated that human spaceflight was no longer science fiction, but achievable reality, inspiring a generation of scientists, engineers, and explorers across all nations. American reaction to Gagarin's achievement catalyzed unprecedented changes in United States space policy and funding priorities. President John F. Kennedy, already concerned about Soviet technological superiority following Sputnik launches, recognized that space exploration had become a crucial arena for international competition. Less than 3 weeks after Gagarin's flight, Kennedy announced the ambitious goal of landing American astronauts on the Moon before the end of the decade, launching the Apollo program that would eventually achieve that objective. The scientific implications of successful human orbital flight extended far beyond national competition to fundamental questions about humanity's future in space. Gagarin's mission proved that Earth's gravitational bonds could be broken not just by mechanical satellites, but by living beings capable of observation, decision-making, and scientific investigation. This capability opened possibilities for human exploration of other planets, scientific research in weightless conditions, and eventual establishment of permanent human settlements beyond Earth. International space law development accelerated following Gagarin's flight, as nations recognized the need for legal frameworks governing human activities in space. The Outer Space Treaty of 1967, signed by major spacefaring nations, established principles for peaceful space exploration, prohibited weapons of mass destruction in orbit, and designated space as the common heritage of all humanity. These legal foundations, inspired partly by the precedent of human spaceflight, continue to govern international space activities today. Technological innovations developed for the Vostok program found applications far beyond space exploration. Life support systems designed to maintain human life in sealed environments, advanced submarine technology, underwater habitat design, and emergency shelter systems. Heat-shielding materials developed for atmospheric re-entry contributed to advances. In metallurgy, ceramics and thermal protection systems used in industrial applications. Miniaturized electronics and communication systems, created for spacecraft operations, influenced the development of portable computers and wireless communication technologies. Educational impacts of Gagarin's achievement rippled through school systems worldwide, inspiring increased emphasis on science, technology, engineering, and mathematics education. Universities reported surges in enrollment for aerospace engineering, physics, and related technical fields, as young people sought to participate in the space age that Gagarin had initiated. This educational emphasis contributed to technological innovation across multiple industries throughout the following decades. Medical research benefited enormously from data collected during Gagarin's flight and subsequent space missions. Understanding human physiological adaptation to weightlessness led to improved treatments for balance disorders, cardiovascular conditions, and bone density problems. Space medicine research contributed to advances in rehabilitation therapy, physical conditioning techniques, and understanding of human adaptation to extreme environments. These medical innovations have helped millions of people on Earth who never intended to travel to space. The psychological impact of seeing Earth from space, first described by Gagarin, fundamentally changed human perspective about our planet's place in the universe. His descriptions of Earth as a beautiful, fragile blue sphere suspended in the blackness of space contributed to growing environmental awareness and the recognition that national boundaries are invisible from space. This overview effect, as psychologists later termed it, influenced environmental protection movements and international cooperation efforts. Commercial space industry development traces its origins to capabilities first demonstrated by Gagarin's mission. Proving that humans could safely travel to orbit and return established the foundation for space tourism, satellite servicing missions, and commercial space stations. Modern commercial spaceflight companies build directly upon engineering principles and operational procedures developed for early human space missions, making space access more routine and affordable. Scientific research in weightless conditions, first made possible by human spaceflight, has contributed to advances in materials science, pharmaceutical development, and fundamental physics research. Manufacturing processes that require zero-gravity conditions have produced ultra-pure crystals, advanced alloys, and pharmaceutical compounds impossible to create on Earth's surface. These applications demonstrate the continuing practical benefits of human space exploration capabilities, first proven by Gagarin's historic flight. The international cooperation in space exploration that began hesitantly during the Cold War has evolved into extensive partnerships exemplified by the International Space Station. Gagarin's demonstration that humans could work effectively in space laid the groundwork for multinational crews conducting collaborative research in orbit, showing that space exploration can unite nations in peaceful scientific endeavors despite political differences on Earth. The 64 years since Gagarin's pioneering orbital flight have witnessed an extraordinary evolution in human spaceflight capabilities, from that single 108-minute journey to permanent human presence aboard the International Space Station. Today, astronauts and cosmonauts routinely spend 6 months or more in orbit, conducting scientific research that would have seemed impossible during the early space age. The ISS, orbiting approximately 400 kilometers above Earth, represents the culmination of international cooperation in space exploration that began with the competitive spirit sparked by Gagarin's achievement. Modern spacecraft design has advanced dramatically, from the spherical Vostok capsule to sophisticated vehicles like SpaceX's Dragon, Boeing's Starliner, and Russia's Soyuz series that continue to evolve from Gagarin's era. These contemporary spacecraft feature advanced life support systems capable of supporting crews for weeks or months, precision navigation systems that allow automated docking with space stations, and reusable components that reduce launch costs. However, the fundamental principles of orbital mechanics, atmospheric re-entry, and human life support that enabled Gagarin's mission remain unchanged. The physiological challenges identified during Gagarin's brief flight have been extensively studied through thousands of subsequent space missions. Long-duration spaceflight research has revealed the full extent of bone density loss, muscle atrophy, and cardiovascular deconditioning that occur during extended weightlessness. Countermeasures developed to address these problems include specialized exercise equipment, resistance training protocols, and pharmaceutical interventions that help maintain astronaut health during missions lasting up to a year or more. Commercial spaceflight, unimaginable in Gagarin's time, has transformed access to orbit from exclusive government programs to services available to private individuals and organizations. Companies like SpaceX, Blue Origin, and Virgin Galactic have developed reusable launch vehicles that dramatically reduce the cost of reaching space. Space tourism, first demonstrated by Dennis Tito's visit to the ISS in 2001, has evolved into suborbital flights that allow civilians to experience the weightlessness and Earth views that Gagarin first described. Scientific research conducted aboard the ISS and other space platforms has produced discoveries impossible to achieve on Earth's surface. Protein crystallization experiments in weightlessness have advanced pharmaceutical development, while materials science research has led to stronger alloys and more efficient manufacturing processes. Earth observation from space, building on Gagarin's first visual reports, now provides critical data for climate research, disaster response, and agricultural monitoring through sophisticated satellite networks. The psychological insights first, gained from Gagarin's mission, have evolved into comprehensive understanding of human factors in space exploration. Astronaut selection and training programs now address not only physical requirements, but also psychological resilience, teamwork, skills, and cultural sensitivity needed for international crews. The overview effect that Gagarin experienced has been studied extensively, revealing consistent patterns of increased environmental awareness and global perspective among space travelers. Future human space exploration builds directly upon the foundation established by Gagarin's flight. NASA's Artemis program aims to return humans to the Moon by the mid-2020s, using advanced spacecraft and life support systems that trace their lineage to Vostok 1. Private companies are developing capabilities for lunar tourism, asteroid mining, and eventual Mars exploration missions that will require many of the same fundamental technologies proven during humanity's first orbital flight. Mars exploration represents the next major milestone in human spaceflight, requiring mission durations of 2 to 3 years and complete self-sufficiency in life support systems. The challenges of interplanetary travel, radiation exposure, psychological isolation, equipment reliability, and emergency response scale directly from problems first encountered and solved during Gagarin's mission. Current research focuses on closed-loop life support systems, advanced radiation shielding, and psychological support techniques for extremely long-duration missions. The democratization of space access continues to accelerate, with multiple nations developing independent human spaceflight capabilities. China's successful crewed missions, India's growing space program, and emerging commercial providers are creating a competitive environment that drives innovation and reduces costs. This expansion of spacefaring nations fulfills the vision of peaceful space exploration that began with Gagarin's mission and the subsequent Outer Space Treaty. Educational and inspirational impacts of space exploration continue to motivate new generations of scientists, engineers, and explorers. Social media and real-time communication from space stations allow millions of people worldwide to share in space experiences, much as television broadcasts brought Gagarin's achievement to global audiences in 1961. Current astronauts conduct live educational events, share photographs of Earth from space, and demonstrate scientific experiments that inspire students to pursue careers in science and technology. The legacy of Yuri Gagarin's 108 minutes in space extends far beyond that single historic flight to encompass humanity's growing presence in space, international cooperation in exploration, and continuing expansion of our species beyond Earth's boundaries. Every human being who has traveled to space since April 12, 1961, follows the path first opened by that young Soviet pilot who dared to slip Earth's gravitational bonds and prove that humanity's future extends far beyond our home planet's surface